Welcome to our lesson to start Chapter 3. Chapter 3.1 is on characteristics of polynomials. Now, you've been looking at certain polynomials for a couple of years now, but a polynomial function is a function that is in one variable and has coefficients multiplying those variables. We've looked up to you have looked up to degree 2 polynomials to this point. This year, we're going to investigate up to degree 5 polynomials. We might talk about some larger polynomials as well, or use some larger polynomials from time to time, but those will be simpler polynomials. But most of our investigations will involve polynomials up to degree 5. So when we talk about the degree of a polynomial, we're talking about the highest exponent on the variable. So usually the variables we use are f of x and x, or y and x. So we're looking at the powers of x. So you've looked at linear functions, which would be a degree 1 polynomial. You've looked at quadratic functions, which are degree 2 polynomials. We've seen a couple of degree 3 or cubic functions this year, not really investigating many of their properties, but just using them to do transformations on. You've also looked at what we could call a degree 0 polynomial, and that would be just a constant function. And the reason it's a degree 0 polynomial is because I could write it as a0 or a0 times x to the 0th power. We know x to the 0th power is equal to 1, so that just gives me a constant function. So that would be something like, if I looked at y equals 5, if a0 was 5. We're also going to further restrict ourselves with the types of polynomials we look at, in that the coefficients and the constants that we see, so the numbers in the equations, we're going to restrict that to integers. We might have a few rational coefficients, but we'll look at we already know how to get rid of rational coefficients, right? If I have a fraction, I'm going to multiply through by the denominator, so I get integer values, which makes life a little bit easier for us. So in the lesson today, we're going to look at a number of different functions. We're going to graph them in Desmos. I've already got them graphed for you. We're going to label some intercepts, maximums, and minimums wherever possible. We're going to describe end behavior for each function. And then we're going to talk about patterns that we might notice in the data tables of the functions as well. You may have looked at this a little bit with quadratics last year, and so we'll build on that as well. So if I start with my first example, we've got a quadratic, we've got x squared minus 5x plus 6. I've got it graphed for us. I already have everything labeled for us as well. In terms of the y-intercept, we know we can grab that c term, or what we would now refer to as our a0 term, or our a0 term, that constant that's added on to the polynomial. That gives us our y-intercept, because if the x's are all zeros, then f of x is going to be equal to 6. If I want to look at the x-intercepts, we know that we're solving for x when y is equal to 0. I can relatively easily factor that expression. So if I'm looking for factors of 6 that add to negative 5, that's going to be negative 2 and negative 3. So when I solve that, I get x equals 2 and I get x equals 3. And I can see that those coordinates are right there for me. Now, because this is a quadratic, we know how to find the minimum. And we could use, we've talked about this a lot recently, we could use negative b over 2a to figure out the x-coordinate of the minimum, and then we could substitute substitute back into the equation, and we could get the y value of the maximum, the y value of the minimum. Obviously, we have a minimum there. But in general, maximums and minimums are for calculus. So in general, max and min of polynomials will be left to calculus. Now, that is only if it's something that we don't already know how to do. Now, for this one, we know how to find that minimum value. We know x is equal to negative b over 2a. So that's going to give us 5 over 12 oh, sorry, 2a, 5 over 2. Grab the 6 by mistake there, which is 2.5. And then we put the 2.5 back into our function, evaluate it, and we'll see that we'll get negative a quarter. And that gives us the value of our minimum. So for a quadratic, we can do that. For something with domain restrictions, we might be able to find maximum or minimum values as well. But in general, we won't be able to find maxes and mins for higher degree polynomials. I want to take a look at the data table for this function now. And I'm going to create what's called a sequence of differences. And this is likely something that you saw last year, but you probably didn't do a whole lot with it. What I'm doing is I'm subtracting 1 point from the next. Oops, I'm getting ahead of myself here. So I'm taking 2 and I'm subtracting 6 from it to get the negative 4. 0 subtract 2 is negative 2. 0 minus 0 would be 0. 2 minus 0 is 2, and then 6 minus 2 is 4. You might be able to see that there's a pattern there. And if I continue and I do what's called a second level sequence of differences, so as I go from negative 4 to negative 2, I can see that at each stage here, I'm increasing those values in the sequence of differences by 2. And what happens for a quadratic, we call this thing that we've just made the second level sequence of differences. Just move that blue box out of the way. So for a quadratic, the second level sequence of differences is constant. Now, this may be something that you talked about last year. This can be very useful to help predict future values. So based on the data table of a higher degree polynomial, if I understand how the sequence of differences works, I'm able to predict values that aren't in the data table. So even if I don't have the equation, but I know that it's a 4th degree polynomial, I'd be able to extend what we're going to talk about today with our sequence of differences, and we'd be able to predict the next term. If I think about sequence of differences with a linear function, when we make a sequence of differences with a linear function, what we're really doing is showing the slope of that function. Now, I should probably step back just a little bit here. The only time I can do a sequence of differences is when I'm seeing that constant change in the independent variable, in that x variable. So that's important to start with, and then I can go through and I can subtract those terms to find the sequence of differences. Okay, the last thing that we need to look at, we'll fill in sort of this area in the middle, we're going to talk about what's called end behavior. And I'll also probably refer to this as limiting behavior, and that's more a connection as we move into calculus. But what end behavior is it tells us what happens to the function at the end of the domain. So what happens as I approach either the top end or the bottom end of the domain. Most of the time, we're going to abbreviate that just as EB. So what I want to know is, as x goes to infinity, what happens to my function? Well, I know this is a quadratic. I look at the leading term. The leading term is positive, or the a value is a positive value. So I know that opens upwards. And that means that as x goes to infinity, the function also goes to infinity. If I look at what happens as x goes to negative infinity, well, then the function goes to infinity, right? This graph is going to continue to grow. And so as I move out to either positive infinity in x or negative infinity in x, that function continues to grow and the function's going to approach infinity. If I had a negative sign, so I had a reflection in the x-axis, right? I had a negative sign in front of the coefficient of my x squared term. We know that quadratic would open downwards, and then in that case, that function would approach negative infinity as it goes. One last thing that I want to look at, I'm just going to trace the quadratic and think about what the possible number of real roots are. So when I have it sitting there, so the quadratic sits across the x-axis, I can see that there are 2 real roots. If I move that quadratic up so the vertex is sitting on the x-axis, sometimes we call this a double root, or we say that there are 2 roots at whatever that value would be. But it means that in terms of looking at the actual value, there is 1 real root. If I continue to slide that quadratic up so it opens upwards and the vertex is above the x-axis, we can see that there are 0 real roots. And of course, if I have 0 real roots, hopefully we know, or we remember, that means that there are 2 imaginary roots. Not a problem for us this year, but it is good to recognize that that's something that exists. So in terms of the properties of this quadratic, we found its y-intercepts, we found its x-intercepts, we talked about the end behavior. So as x approaches either positive infinity or negative infinity, the function is approaching infinity. We looked at the minimum of this function, and we said in general, minimums and maximums are a calculus 12 problem. But if it's a quadratic, we know how to find the coordinates of maximums and minimums. If I have a data table, we looked at the patterns that we see in the data table, ensuring, of course, that we have a constant interval in our x's. We can then see that the second level sequence of differences will be a constant for a quadratic. All right, let's move on to our next example. So this time we have a cubic. Now with this cubic, all we really need to do is to look at the graph that I have. I'm going to show you where the x-intercepts come from. The y-intercept is pretty straightforward, hopefully. Again, we can see that y-intercept just comes from the constant, because our x values, if all our x values are 0, then the y-coordinate of that function is going to be equal to 6. Let's start by looking at where those x-intercepts came from, because we actually know enough to do this already. What I want you to notice is that I have some sort of factoring going on here, and I can factor by grouping. So this is one of the factoring methods that you looked at last year. It's not always one that people are super fond of, maybe. But if I look at those first 2 terms, I have a common factor of 3x squared in them. So if I factor out the 3x squared, I'm going to get an x minus 2. If I look at the next 2 factors, I'm going to factor out a negative 3 from the negative 3x and the plus 6. So if I pull out that negative 3, that's also going to leave me with an x minus 2. All right, so now I can do some common factoring. There's a common factor of x minus 2 between those terms. That leaves me with 3x squared minus 3. I can pull out a 3 from that second set of brackets. And that gives me x squared minus 1. And even though this is a higher degree polynomial than we've dealt with before, we still know how to find the roots. I just need to set those terms equal to 0 and solve for x. So I don't need to worry about the constant, because 3 can never be equal to 0. But I could have that x minus 2 is equal to 0. And so that gives me one x-intercept at x equals 2. So there's that one. I could have x squared minus 1 is equal to 0. Add the 1 to both sides. I can take the square root of both sides of that equation. And that's going to leave me with x being plus or minus 1. And I can see there are my other two x-intercepts. So I've got all three of my x-intercepts simply by factoring. When it comes to higher degree polynomials, we can't just factor using decomposition. So in this case, we had to factor by grouping first, and then we were able to further factor. If you wanted to, I guess I just solved, but if you wanted to, that x squared minus 1, you always could have rewritten that as x plus 1 and x minus 1, because we should hopefully recognize that as a difference of perfect squares factoring. With the x squared in there, it's just about as easy, maybe even a little more time efficient if I just take the square root of both sides there and get the x equals plus 1 and negative 1. I've labeled the maximum and minimum for you. You can see those are not nice values, and those aren't values that we're going to be able to come up with algebraically right now. Again, we're going to have to wait for calculus. It's not that it's an overly hard procedure. It's just that we need to understand some calculus before I can find maximums and minimums of higher order polynomials. We're going to change our order a little bit. We're going to look at the end behavior. Now, we based our end behavior last time mostly on the graph. This time, I'm going to look at it algebraically as well and sort of back up what we see with the graph. When it comes to end behavior, the only term I really care about as I approach infinity is going to be the term that has the highest power on x. Because if I'm looking at a really big number cubed or a really big number squared, it's the number cubed that's going to dominate. That's going to give me the behavior of the function. So if I look at that 3x cubed, if I cube infinity, or I cube a great big positive number, I'm going to get a great big positive number, right? A million cubed is going to give me a million times a million times a million. It's going to give me a positive number. And so I can tell algebraically by looking at that leading term that as x goes to infinity, the function is going to approach infinity. If I think about what's going to happen as x approaches negative infinity, so as I move to the left on the graph, well, a negative times a negative times a negative, when I look at cubing that great big negative value, is going to end up with a negative value, which means that the function is going to be approaching negative infinity. I can see that's reflected in the graph as well. As x continues to grow in the negative direction, this function is going to become more and more negative. As x grows in the positive function or positive direction, the function is going to become more and more positive. All right, let's take a look at our data table now. I'm hoping some of you have an idea of what to expect when we look at our sequence of differences here. All right, so I'm dropping by 6. I've got 0. I'm increasing by 24. I'm increasing by 66. That doesn't seem like there's any nice pattern here. I'm increasing by 126. All right, let's go to our second level difference or sequence of difference here. So I increase by 6. I increase by 24. I increase by 40. And I increase by 60. So I go one more time, and I'm going to increase by 18. I'm going to increase by 16, and then I'm going to increase by 20. And I think I had a mental math mistake somewhere here. What did I do? Oh, I see it. Sorry about this. Let's just fix these last couple. 24 to 66 is 42, sorry. Okay, and then I had 60, and that's going to make life so much better for us. Because now I'm seeing what I hope some of you had seen in the first place. It's too close to the edge of my screen here. But 42 minus 24 gives me 18. 60 minus 42 gives me 18. And I can see that I get a constant in my third level sequence of differences for my cubic. So what we can imply from this is that depending on the order of our polynomial, that's going to tell me where I'm going to see a constant in my sequence of differences. And so what I can use that for, I had mentioned this earlier, what if I want to know what f of x is equal to when x is equal to 6? Well, I can work my way down there because I know the next number along in the second level sequence of differences is going to be 18 more than 60. And so what that also tells me is that in the next term here, I need to go to 126 plus 78, which gives me 204. So it'll be 204 more than 216, which is going to be 420. And so I can evaluate that value of the function without actually going through and putting the value into the function. Not that we couldn't do that too, so I'll just open the calculator here and we can take a look at that as well, just so we can see that we're going to get the same value there. So I'll open this up, or we'll wait for it to open up, I guess. Scroll back up here so we can see the function. We wanted to figure out what f of 6 was going to be. Calculator doesn't want to seem to move for me here. So we had 3 times 6 cubed minus, get my cursor out of the exponent there, minus 6 times 6 squared minus 3 times 6, and then plus 6. And we can see that that's 420. All right, so let's go look at one more example. So this time I'm giving you a cubic, but it's already in factored form. What's different with this cubic, well, there's a couple of things different with this cubic, but it looks like there's only one real root this time. Now, in that last example, we didn't talk about the possibilities of real roots. So maybe we'll just jump back really quickly and do this. But if I trace that cubic and I grab my cubic and I look at it, sitting like this, I'm going to have 3 real roots. If I pull that cubic up, so the vertex happens to sit right on the axis, I'm going to have 2 real roots. And if I pull it up some more, if I just picture it being extended some more down there, I can see that I could have 1 real root. But because of the end behavior, because the function goes to, it looks like I drew over this earlier. Let me fix my end behavior here. We said that function was going to negative infinity. As the function goes to negative infinity, as x goes to negative infinity, and the function goes to positive infinity as x goes to infinity, if I think about that, that means that at some point, I know I drew a linear function there, but if I end up down here and I end up here, that function has to cross the x-axis at some point. So there is no way with a cubic function to be able to have only 0 or only imaginary roots. I have to have at least 1 real root. So what happens with a cubic function is I can have 1, 2, or 3 real roots, but I have to have at least 1. With our quadratic, we were able to get 0 real roots by pulling that vertex above the x-axis if the function opens upwards and below the x-axis if the function opens downwards. When I look at this one, I can see that I still have 1 x-intercept, but there's something going on in terms of the algebraic expression of the function, that's going to show me why I don't have more than one real root here, why I don't have more than one x-intercept. So let's start there. Let's set that equal to 0 and see what we've got. So we've got negative x plus 1 times x squared plus 1 equals 0. So that means that x plus 1 is equal to 0. I can solve that. There's no problems there. That gives me x is equal to negative 1. There's the x-intercept that we already have. If I look at the other factor, I've got x squared plus 1 is equal to 0. Subtract the 1 from both sides and we can see where the problem is. X is equal to plus or minus the square root of negative 1. And we can't do that, right? That is imaginary. Because I'm trying to take the square root of a negative number. And so in this case, this function only has one real root. If I think about how to get the y-intercept by looking at the algebraic expression of it, when I multiply through the x plus 1 times the x squared plus 1, I don't have to actually multiply all the terms out because the constant's going to come from the 1 times 1, and then there's a negative sign out in front of it. So 1 times 1 gives me 1, times negative 1 gives me negative 1, and there's my y-intercept of this cubic. If I look at the end behavior, we can see that the end behavior has changed slightly as x goes to infinity, because again of that negative sign out in front, I'm going to have negative infinity times infinity times infinity, right? Or negative big number times big number times big number, which is going to give me a negative value. So the function is going to approach negative infinity as x approaches infinity. If I think about what happens as x approaches negative infinity, so as I start approaching big negative values, I have a negative times a negative times a negative, which is going to give me a negative value. But again, we've got, don't forget that negative sign out in front. And so in effect, I have 4 negative signs, which is going to give me a positive value. So the function is going to approach positive infinity. If I look at my sequence of differences here, we're going to run through it just to make sure we can see that the same thing's happening. Things are getting more negative as we go. So I've got negative 3, negative 11, negative 25, negative 45. And then what do we have? 156 minus 85 gives me negative 71. All right, so then I've got negative 8, negative 14, negative 20. You can probably see we're starting to get a pattern happening here. That's negative 26. I'm going to just grab this rectangle here and try and get it a little further out of our way. So negative 8 to negative 14 is a change of negative 6. Negative 14 to negative 20 is negative 6. And negative 20 to negative 26 is, my laptop doesn't like me writing there, but that's a negative 6 as well. So I don't have any maximums or minimums in this one. So we can apparently change cubics so that I don't have maximums and minimums. If we jump back again to example number 2, we saw that there was a maximum and a minimum in this one as I'm looking at the behavior of that cubic function. I don't have that in example 3, but that's okay. Sometimes that's going to happen. Again, that's going to be a problem for calculus for us to find out when we have maximums and minimums, where they are, and when we don't have maximums and minimums. Okay, so we've looked at a quadratic and 2 cubics. I'm going to give you a quartic function. So that's a function, if we expanded this out, you don't need to expand it all the way out, but it would have a highest power of x to the 4th, or highest power of 4. So it's a degree 4 polynomial. I want you to label the roots of the function and the y-intercept. I've given it to you in factored form, so that should be relatively straightforward. I want you to describe the end behavior of the function. I want you to look at the sequence of differences. Hopefully you have a pretty good idea of what's happening at this point with that sequence of differences. So it'll really just be going through it to make sure that you can see that. And then I want you to think about how many real roots are possible for a fourth degree polynomial. So given a graph that's going to look maybe something like this, and you can play around in Desmos if you want to, I want to see what those possibilities are for the real roots. All right, if you have any questions, make sure you have them ready for our next class and we'll talk about them then. Good luck with your example.